Hi everyone, and thank you for being here. My name is Youngjoo, and I'm really excited to share my work, Click to Hack, fudging and exploiting browser beyond mouse clicks. So before we begin, let me introduce myself. I'm from South Korea, and I'm a master's student studying computer security at Seoul National University. And I really enjoy playing CTFs with my team, the Rector Rhine. And I played a lot of CTFs, such as the DefCamp like that. And my passions includes the code auditing and fudging and exploitation. And my favorite target is the browser. So today's agenda is UI bug exploit and fudging in the browser. I will show you how these bugs can be exploited and how I make a fudger to find them. And I also received $40,000 in bug bounties from the Google, and I will show you the bugs that I found at the end. So let's start by looking at how web browsers are designed. Modern web browsers are generally built around two main types of processes. The first one is the browser process, which handles overall tasks like the UI, network, storage, and permissions. Then each tab has its own renderer process, which takes care of rendering content. This includes parsing HTML and CSS and executing JavaScript. That's why when you open many tabs, you see multiple processes running in your system. So the browser process and renderer process are separated, but why these separations? There are several reasons, such as security and stability and performance. For now, let's focus on the security benefits of this design. So this is an overall pictures of the browser process and the renderer process. As I mentioned before, the renderer process is isolated at the tab level and also separated from the browser process. This separation is enforced by the browser's sandbox mechanisms. The sandbox prevents a tab from directly accessing system files or retrieving information from other tabs. So by limiting its system calls and giving the low permission to each process, they protect this kind of the attacks. So you can see that only the browser process has direct access to the system and other tabs. So let's assume like one tab gets compromised by the attacker, such as when a user clicks on a malicious website. We can see the attacker in the tab 3. And if there is a vulnerability in the renderer, the attacker could use many features to trigger the vulnerability, such as like learning JavaScript or like parsing crafted malicious HTML. And if the attacker successfully exploit the renderer, they can execute any code they want within the renderer process. However, even if the attackers gains code execution within the renderer process, they cannot directly access the system files or view data from the other tabs. This is because the renderer process has a very low permissions and they limit some of the like unnecessary syscalls. So to compromise the entire web browsers, the attacker would need to escape the sandbox. This means the attacker should find additional vulnerabilities to break out of the sandbox, typically by targeting the IPC between the browser process and the render process, or by like exploiting OS vulnerabilities. But using OS vulnerabilities are very limited because the sandbox restricts the unnecessary system calls in the render process, and also there are very few IPC calls. This makes the attack surface very small, making sandbox escape challenging. But think about this, like what if we could exploit the browser process directly? This is possible using a UI bug because the UI bugs occur in the browser process. This means we can exploit the entire browser with a single vulnerability and no need to find multiple vulnerabilities or chain exploit together. So even though UI bugs require user interaction to trigger, they can have a significant impact. Today, I will show you how we can exploit the browser directly using a UI bug. So, what is the UI bugs? UI bugs means an unintended flow in the visual or interactive element of an applications. Like, have you ever had lots of tab open or loaded a complex website? Like sometimes this can cause one or more tabs to freeze or stop responding and forcing you to refresh the page. So this is a simple example of a UI bug, and most bugs like this simply reduce the usability. Because of that, they're usually considered as minor issues, but what if a UI bug could lead to the memory corruptions? For example, when we click on the browsers, it crashes. So the most memory corruption bugs are potentially exploitable, but do you really think this UI bug could be exploited? So the answer is very difficult, because the UI input doesn't allow for meaningful data such as memory addresses or shortcode, which are typically essential for exploitations. So if the UI bug immediately changed the control flow right after it's triggered, like a stack flow, it isn't useful for exploitations because there are no chance to input meaningful data right afterwards. However, with something like a user-free bug, where there are multiple steps between triggering and exploiting, we gain the time needed to insert our input. So this gives us the ability to manipulate memory using JavaScript after the bug is triggered. So we will only consider the user-free bug today. And yeah, let's dive into the UAF. The user-free bug, or UAF, happens when a program tries to use memory that has already been freed. I will show you the scenarios that explain how a UAF bug is triggered in a normal C or C++ program. Let's start with an empty memory space. So when we allocate the dynamic memory, an object is created in the heap memory, and also the pointer is created, which represents the object. And then, if we decide the object is no longer needed, we free the object, releasing the memory back to the system. This memory region becomes available for future allocations. In the free steps shown here, you can see a pointer still referring to the freed object. And this is the important condition for a user-free bug. The pointer should refer the freed object. But no unintended behavior happens until the program actually tries to use that pointer. But once it does, the program can behave unpredictably. So in summary, the issue arises if the program still holds on to the pointer to the freed memory and try to use it again. Since the memory is now free and could be reallocated for a different purpose, reusing this pointer can lead to unintended behavior, and this is the user-free. So, and that point is where an attacker can exploit a bug. Like, they can reallocate the memory with their own data, taking control of the program's actions when the pointer is used. This is why I say UAF has distinct steps between triggering and exploiting the bug. It doesn't make any unintended behavior before the use. We can manipulate the memory with the JavaScript after the bug is triggered. So that's why I focus on exploiting the use after free bugs for UI bug. Now let's look at the other consideration of for the exploit. The first, we need to think about the inputs involved. There are two main inputs, the UI input from the user and the JavaScript input controlled by the attackers. Because the user's input triggers the vulnerability, the attacker needs to trick the user into interacting, often by using phishing to get them to take specific actions. So this is quite a hard constraint of the exploit. So the triggering the vulnerability can be significantly different depending on the bugs. So as for the JavaScript input, when a user visits the attacker's website, the attacker can execute any JavaScript code to manipulate memory as needed. However, since JavaScript is executed in the render process, we still need to figure out how to allocate the memory from the render process to the browser process. But I will cover that part in detail later. And one other important note is we don't need to worry about the browser sandbox itself because the bug occurs within the browser process, not a render process. So if the attacker successfully exploit the vulnerability, they can get a full access of the browser. So this is also like another consideration of the exploit, and we are focusing on the user of the free bug. It's important to understand how allocate and use and free operation impact the bugs. Since we have two inputs, we need to identify which input influences the UAF trigger stages. For example, using 3 clicks can handle like allocation, free, use steps, like a first example. But if we can free the object with the JavaScript, only 2 clicks are needed, like a second example. So that means like a fewer clicks make the exploit easier to perform, increasing its potential impact. So yeah, let's go over a detailed example of a UI UAF exploit. So first, let's assume that triggering the vulnerability requires 1 click to allocate the heap object and 1 JavaScript actions to free the object and another click to use the pointer that refers the freed object. And the process starts with the victim visiting the attacker's website, which is a common first step in browser exploit. Then second step is allocating controllable objects over and over again using the attacker's JavaScript. Since the victim has opened the attacker's website, the attacker can execute any JavaScript they want. The reasons for this repeated allocation is for the object reallocations. Repeated allocations are important for object reallocations because like in typical user of the free exploit, attacker should reallocate object with a specific data to exploit the vulnerability. But here, the attacker doesn't know exactly when the vulnerability will be triggered or when the object will be reallocated. So they keep allocating until the object is eventually reallocated after the bug is triggered. And the third step is inducing the victim to click the GUI element to allocate the target object. Because we are assuming the object allocation occurs when the user clicks some GUI element. And this target object in here means the object that will be freed and accessed later by the user of the free bugs. So this is a kind of tricky part because the attacker needs to make the user into clicking. But you might ask, why not just click the button automatically with a JavaScript? Because usually the button that caused the vulnerability is in the outside of the renderer. That means we cannot click that button with the JavaScript or like something in render side. So that's the reason why we should make user to click the some buttons. But in our example, we make a button labeled click me, assuming the victim will click it. These inducing actions might significantly differ based on the specific bug, but yeah. And when the button is clicked, the target object is created in the heap memory with a pointer referencing that object. This is the allocation stage in the user-free attack scenarios. But keep in mind that although it is not shown in the slide, the JavaScript from the previous slide is still learning, allocating many spread objects. And the next, the attacker frees the object using the JavaScript code because we also assuming we can free the target object with a JavaScript. So after the target object is freed, some pointers still reference it. We call this pointer the dangling pointer, and this is the core condition for the use of the free. However, at this point, the program didn't do unintended behavior because the dangling pointer has not actually been used. This is why the program remains stable after this free. And the next, the attacker reallocate the target object as a sprayed object using the JavaScript code that has been running from the beginning, constantly creating a numerous sprayed object. This is why the attacker starts the JavaScript as soon as the victim opens the website. Since the attacker doesn't know exactly when the target object will be freed, they keep executing the code repeatedly until the target object is reallocated. The attacker can fill the sprayed object with their own data, and the dangling pointer will now point to that object containing the attacker's desired input. But there's still one final step left. The final step is also inducing the victim to click the GUI element to trigger the use of dangling pointers. Because we are also assuming one click is needed for use. This action causes the program to access the dangling pointers, which now represents the attacker's sprayed object, reading the program to behave as the attacker's intent. Additionally, when this pointer are accessed, the access pattern determines how this bug is exploited. In the example of the left, a heap address is written to the target object, which results in a memory leak. In the example on the right, data is read from the target object and used in the core instruction, causing the control flow hijacking. This shows how different access patterns let attackers exploit the vulnerability in various ways. And that's the 4 scenarios of how UI-based bugs can be attacked in the browsers. So now let me show you a real-world example. These bugs follow the same patterns as the one I showed you in the UI exploit scenarios. The allocation happens when the user right-click on the URL bar, and the attacker can then free the UI object using the JavaScript code that closing the window, the tab of the browsers. And for the use part, the victim simply moves the mouse cursor over the right-click menu. So in total, exploiting this bug requires 1 click and 1 JavaScript code and 1 mouse movement. I believe this is realistic scenarios for real-world exploits, since the action needed to trigger the vulnerability is quite simple. So this is the script for heap spraying, and this code executes when the victim opens the attacker's website. In this case, I use the blob to allocate the heap memory in the browser process. The attacker can allocate any size of chunks using a blob and can read or write it freely. Since the target object size for the UAF is 0x100, we use 0x100 as the size for the sprayed object. And for the demo, I will fill the blob's contents with the letter A, which has an ASCII code of 0x41. And also, this is the use pattern. You can see that the RAX is changed to the 0x41, 41, 41, 41, and the program crashes at the code instruction at RAX plus 0x18. This indicates that the attackers can achieve control flow hijacking through this vulnerability. So I will show you the demo of the control flow hijacking with CBE 2022-0295. For this demo, Chrome is built with tcmalloc instead of the partition allocator. This is because the partition allocator isolates the blob allocation in the browser process. Bypassing certain attack mitigation in the allocator is beyond our scope, so I use the tcmalloc to demo, and I will show you about that. Okay. Oh. Okay. So it's quite dark. Yeah, so the first step is open the Chrome browsers, and you can see the page. And this is for attaching GDB to Chrome browser to see the memory after it crashed. So yeah, this part. And we are assuming the normal user, click the link and in the red box, and that link is to the attacker's website. So click the link. And you can see the window that is popped up is the background JavaScript code that is for the heap spraying. I mean, the allocating a lot of heap objects using that. But I just make it visible for a demo. I mean, but I can hide in real exploit. But yeah. And also, you can see the page, and the page says, please right-click on the URL bar. And we're assuming the victim, click the URL bars here with a right click. And yeah, victims are right-click on the URL bar, and we can see the right-click menu. And that time, the attacker can close the tab with the attacker's JavaScript like this. And then the victim should move the mouse cursor to that right menu. So this is the condition of the vulnerability and is severe vulnerability. And if so, the cursor doesn't appear in my screen, but I actually moved the mouse cursor to the right menu, and you can see the browser is crashed, and GDB caught the crash. And when I see the register, the RAX is 0x41414141, and that means we can override the RAX register with our desired input. And also the RIP refers to core instruction with the RX register, and that means we can exploit this bug with a control flow hijacking. And this looks kind of complicated, so I just show you without the video editing. So yeah, click the link and popped up. And the user is just click the right button on the URL bar and just move the mouse cursor to the right menu, and that's all. And it get crashed. So yeah, this is the real world exploit, the demo of that. And okay. Okay. So yeah, let's dive into creating a fudger for finding this kind of UI bugs. A good starting point is these questions. How is UI fudging different from the traditional file fudging? Of course, the input is clearly different. A file can be passed all at once, since it's just one file. But with the UI, specifically for mouse clicks, there is a sequence to consider. And they cannot all be processed simultaneously because the normal user click once at a time. The outcome also depends on the sequence of clicks. However, even if the click sequence is the same, processing timing can be different. And it is a major issue in UI fuzzing. So let's dive into the timing issue here. So first, assume the order and the location of the click are the same. This means the location referred to by the clicks doesn't change in the two running example. However, the timing of when the event was sent is slightly different, as shown in the pictures. In the first run, clicks are sent at 0, 10, 20, and 30 milliseconds. And the second run, we are sending at 0, 20, 30, and 40 milliseconds. But do you think this would produce the same result? Probably not, because the layout of 10 milliseconds at the 20 millisecond can be different. So even if the location is the same, different behavior can occur. But what if we send all mouse clicks at exactly the same times in both the first and second runs? Will that guarantee the same outcomes? And surprisingly, the answer is still unclear. Even with the same clicks and at the same times, we cannot ensure the program will handle in the same way at the same time. Let me illustrate this with an example. So we have a simple program here. Each time you click a button, it generates a new button. So it's pretty basic, right? And let's start by clicking button A at the 10 millisecond like this. This click will generate a new button B, and now click the new button B at 30 millisecond, and it also creates a new button C, and as a result, the C button appears at the very front. So yeah, that's the first run, and now let's start the second run. So the initial state is same, and clicking the button A at the 10 millisecond is also same. But here's the difference. The click should be processed within 10 milliseconds, but it is not. At the 20 millisecond, it's still processing our click, and we don't know exactly when it will finish. So in 30 milliseconds, we will send a mouse click at the same time in the same spot as the first run, but our mouse click will be ignored because there's no button B's now. So then at 40 milliseconds, the processing of the first mouse click is complete, creating button B. So the outcome is different comparing the first run, even though we sent the same mouse click at the same times as in the first run. So this processing delay is affected by many factors like delayed task or CPU load, making the timing unpredictable. We also don't want to add long delay between inputs, as this would create a significant overhead for the fuzzing. With the existing overhead from sending input one by one at a time, adding more delays would make it even heavier. So this ambiguous processing timing is a big issue of UI fuzzing. And then there's another issue here. Randomly generated inputs are almost useless. For instance, when you open the browser, the layout might look like the picture here. How big is the area where a left click would work? So probably just a small sections. Now imagine we are sending mouse event to randomly generate coordinates. So we might notice that many events are ignored because the meaningful region of the layout are really small. So usually in fuzzing, this is not a big issue because we can send the large size of the input at once. Instead, we have, but for the UI input, we cannot send them all at once. Instead, we have to send them one by one. This means we need to put delays between these mouse inputs. If there are too many inputs, the execution time will become very long, which significantly impacts the fuzzing performance. So we should avoid sending meaningless input. So let's summarize the characteristic of UI input. The first, like file fuzzing, we need to introduce delays between inputs because each event is processed by one. Without this delay, the program might not handle the input properly, and also it might be not able to use in real-world scenarios because the normal user usually click once at a time. Second, the order of inputs matter a lot. Changing one input can completely change how the following input are processed because the layout or changes dynamically based on prior event. Third is it's really difficult to pinpoint when an input is fully processed. This is not only complicated with reproducing the bug, but also make it hard to use the coverage feedback effectively. And last, if we use random generate event in fuzzing, most of them will likely be ignored since many parts of the layout are not meaningful. So considering this, how can we mutate the input for fuzzing? So usually, the coverage guided is well-known technique for fuzzing, but it is not the best here. The most important reason is that we cannot pass large input at once, which make it take a significant amount of time to reach complex state. So I suggest the new approach to fuzz based on layout guide. It works like this. So first, we find all the layout in the browsers. Then we pick one among the new layout and send to the mouse click on it. If this click changes the layout and send to the, we repeat the whole process like finding all layout and finding which one is new layout. So this let us dive deeper into the browser state. So if we do like that, most input might make some of changes to the program. Then also we are recording all coordinate of the layout and we are giving a high priority to the newly generated layout. So it makes the program to go deep inside, which leads to reach the high code coverage. And otherwise, if the click doesn't cause any changes to the current layout, we lower its priority and pick a higher priority one instead. This helps us target layouts that are more likely to lead to a complex state. And also, you can see the first example, we are clicking the red box, the reload button, but it doesn't affect any layout, so we give the lower priority to the reload button like this. So using this technique, we don't need to restart the browser to measure code coverage and allow us to dive deeper into the browser state. And we also created a reproducer to address the ambiguous timing issues of UI inputs. The problem is that sending input in the same order can sometimes lead to different outcomes, right? So by recording our event handling inside the browser during fuzzing, we can observe how each input is actually processed. This way, we know exactly which events are processed and how they are processed. So, for example, in this example, we can exactly know whether the third click was processed or not. If it was processed, we can also identify the exact code executed for that event. With this information, we can accurately reproduce the bug, eliminating any ambiguous input. Now let's move to the real implementation details. I tried many techniques to fetch the browser layout, but in the end, I decided to directly insert code into the Chrome browser. Layout are usually created in the square shape, so by inserting code into the layout initialization process, I could know the exact coordination of the square shape of the layout and the layout tree. The key of fetching layout is identifying clickable layout because we want to avoid meaningless layout. So we focus finding the layout that can accept the mouse clicks. Next, we select layout with a higher priority. As I mentioned earlier, we send event to the newly generated layout following the layout guided approach. Then the event senders send an event to the selected layout. And that's it. So quite simple, right? But we just repeat these steps, fetch the layout, select the layout, and send the event. However, it's important to note that we record information during fuzzing to reproduce the bug. So we record 3 information in the fuzzing loops. the selected layout, and the generate event, and the sequence of the event handler in the browsers. Let's start with the selected layout. It literally means the layout we selected with layout guiding approach in the fuzzing loop. And generate event is also the event we sent in the fuzzing loop. And we are also recording the sequence of event handler in the browsers. Event handler generally start with a bigger layout and move to smaller ones. So we are record entire process of handling. To make this possible, we added code to the browser's event handling code. And this let us see exactly which handlers are involved and in what order. Okay, so that's the recording part of the fuzzing loop. Now let's dive into how the reproducer works. So when we found the crash, we load the logs recorded during the fuzzing loop. These logs include the selected layout, generate event, and the sequence of event handlers. At first, we use the selected layout to check if the same layout exists in the current browser layout. And if it doesn't, we restart the browser and begin the reproducing process again. And if we do find the same layout in the current layout, we move on to the next step. So next is very simple. Just send with the same event that was sent during the fuzzing loop. And this is the final step. So comparing the sequence of event handling. After sending the event, we record the browser's event handling sequence again. Then we compare the sequence with the recorded event handler logs. If they match, we go back to the first step and repeat the process. So if they don't, we stop the restart. We stop the whole process and restart the reproduction process. So that's it. We repeat this process until all the logs are processed and the crash occurs. Additionally, there are minor adjustments made when reproductions fail, such as increasing the timing between specific input or removing meaningless inputs to make the logs smaller. And using this system, we can successfully reproduce the bugs found during fuzzing. So this is the result, and actually the duplication bugs are more than 4, but yeah. And I also find 6 bugs, and they have been fixed. And 3 bugs in the Windows and 3 bugs in Chrome OS. And also I can get bounties from the Google VIP. So I will show you guys about the bug that I found. Okay. So this is the first bug example, and it's really like interesting because okay, start with the opening the browser, and we are going to crash the browser. So like usually the reason of the crash is memory exhaust like this. So you might see this page when you're using the browser. So we can make this state easily, like allocating a lot of heap object like that. So we assume the big teams in like this state. I mean the crash state in the render, and we're open the browsers, open the task manager of the Chrome. So there is the task manager to like manage the renderer, and if we open the task manager, it crashes, and all the sanitizer can get a crash. So yeah, this is the one, and I think it's quite realistic because the crash state can be easily made by the attackers, and so but we still need some way to user to click the task manager, but yeah. And this is the really simple example, and the one of the maybe duplicated one. And this is really simple. Like when you click the microphone, the browser give me like this type of permission check, like you want to allow or block. So when I just click the block, it got crashes. So this is also like kind of like realistic scenarios. And yeah, I will show the last one. And this one is not that realistic one. So this is quite like interesting. So you can change the color of the browser with a setting. So like just click the color of the browser and repeating this click, and at some time just close the browser like this, and it will cause the user to free. So I believe this is not a like unrealistic one, but so for the UI box, the user interaction is really important because it is like decides this box can be exploited or not. So okay. So lastly, I'd like to discuss what makes it harder to exploit UI bugs. The first challenge is the UI interactions. As we've seen, if the required user interaction is too complex, it becomes almost impossible to trigger the bug naturally. And the second challenge is object spraying. This is difficult because to exploit a vulnerability in the browser process, you need to allocate memory from the renderer to the browser process. In our demo, we use the blob API to allocate memory, but in modern Chrome, the partition allocator separates blob memory from other memory in the browser process. So this means you need to find different way to allocate memory, and it can be different depending on the type of the browser and type of the box. And such allocator mitigation makes exploitation much harder. And additionally, there are exploit mitigation like a mid-bucket pointer, which protect against user-free vulnerabilities. To exploit this, you need to bypass these mitigations. But this isn't just a challenge for UI bugs. Bypassing this type of the mitigation is essential for exploiting any hip user-free bug. So yeah, this is a summary. So in summary, it's important to note that UI bug in the browser can be exploited. And to find these bugs, we can use the fudger that follows layout guide approach. And once bug is found, a log recording system helps us reproduce it reliably. So yeah, that's my talk. And if you have any questions, like give me or just using the QR code, you can contact me. Yeah, thank you.
Thank you so much, Young. I already see a couple of questions here and one there. One in the back also.
What's up, next line? Dope presentation. So I was just wondering, because it sounds to me like the fuzzing process is quite slow. So how long did it took you? How long did you have to let the fuzzer run until you discovered all these vulnerabilities?
Sorry, I cannot hear.
So can you hear me now? So I was just wondering, because it sounds to me like the fuzzing process is pretty slow. So I was wondering, how long did you let the fuzzer run until you discovered?
Maybe 2 weeks, I guess. Maybe, yeah. 2 weeks, 1 week, because I just improved the fudger. Like when I running the fudger and I just improving again and again the fudger. So the time will be might be 1 month, but yes, it's like for the fuzzing time, it might be like 1 week or 2 weeks. Yeah.
Okay, so you
Yeah.
showed the bug with the task manager.
Sorry.
The bug where you had to open the task manager. Does it also work with the keyboard shortcut instead of having to click the UI?
Sorry, I cannot.
So you
yeah.
have the bug with the task manager.
That's
That
what?
task manager where you crash the tab with a memory, memory allocation failure, like out of memory.
Yeah, the memory.
Yeah. So then you open the task manager to.
A task manager, you mean?
Yeah, yeah.
Ah, yeah.
Does it work with the keyboard shortcut as well?
Ah, yeah. I mean, you mean like we cannot execute any JavaScript in the crash state, or?
I mean, you showed like the
Yeah.
the click where you had to open the task manager, but there's also a shortcut to open the task manager in Chrome. So could you use the shortcut instead of having to open the task manager manually?
Ah, you mean the shortcut?
Yeah.
Yeah. So yeah, also the shortcut can be used in the exploit, I guess.
Okay.
And sorry, I can.
Maybe you two can meet after we take a couple more questions and discuss this. We have something here in front, two questions actually.
Yeah, great presentation. When did you start finding bugs?
Sorry, how?
When did you start finding bugs in Chrome? And
This one.
yeah,
I mean,
in Microsoft.
maybe 2 years ago. 1 year ago, 2 years ago. It's quite a long time ago. Yeah.
Okay, thank you.
Yeah.
We have one more question here in the front, and we'll take one more on the right side, and then we take a 5-minute break.
Hi, thanks
hi.
a lot. Really, I really enjoyed your presentation.
Thank you.
Fantastic, really amazing. I have just one question, which is that, so we are talking about Chrome here, but I don't know if you looked into other browsers, Firefox, Safari, etc. Have you ever looked like if there's like bugs like this, or like what's the prevalence? Like, do you think like there's like a browser that has like more bugs than others, or you know?
Yeah. I believe I didn't try for the other browser, but I believe the other browser have some more bugs than the Chrome, because I think Chrome is really safe, and a lot of the mitigation is for the heap user free. Like, but the other browser there are no that kind of the mitigation yet. So maybe we can I can find more vulnerabilities in the other browser. But the condition is the browser should open source to fetch the layout and like add some like handlers logs, and also and you should like engineering like implementation for each browser, and it take a long time. So maybe we can try the other projects, other browsers, but I didn't try it yet. Yeah.
Thanks a lot. Great presentation. Great.
Yeah.
answer.
Thank you.
Thank you.
Thank you.
So there was one more question on the right side. I said one more question. Sorry. Oh. Yes, there. He was first, yes. Okay.
Thank you for your presentation, first of all.
Thank you.
My question is, since user interaction seems to be critical for this exploit, is there any way to mimic that through JavaScript code?
So did you ask what is this for? The exploitation for, or?
No, no. So can you mimic user interaction through JavaScript code to bypass the user having to click?
Yeah, yeah.
Yeah?
So, yeah. So you mean we can use the JavaScript to induce some users interacting, right?
Yeah, yeah. Can you mimic through JavaScript user interaction? Like having to click the actual button.
Yeah, you mean like making some user interaction with a JavaScript, or?
Yeah, in the code, in the actual script.
Yeah, that's right.
Yeah, could you mimic the user interaction?
Yeah, I mean, it's impossible, I think, because like the box is, I mean, the button, like the vulnerability is outside of the renderer. So you cannot like make any user interaction with like the code, like a JavaScript like that. So it's impossible. So the user should click with their own. So yeah, this is quite hard constraint for this exploit. Yeah.